You're somewhere you've never been. You open your phone, and a little blue dot already knows exactly where you're standing. To within a few meters, anywhere on the surface of the Earth, in a second or two. It does this by listening to faint whispers from clocks flying 20,000 kilometers overhead. Atomic clocks in orbit. And to get your position right, those clocks must be corrected for one of the strangest facts in physics. That time itself runs at different speeds up there. GPS is quietly a working proof of Einstein's relativity, running in your pocket. So let's build it from scratch, one idea at a time, and see how a blue dot is really a small miracle. Forget satellites for a moment. Here's the core puzzle. If you were truly lost, how could you possibly pin down your exact position? The key is reference points, places whose location you already know, and your distance to each of them. But distance from a single known point isn't enough. It only tells you you're somewhere on a ring around it. To find one spot, you have to combine several. So the whole game becomes known points, known distances, and a little geometry. Sailors leaned on this for centuries. 2 landmarks, 2 bearings, and you fix your spot on the chart. GPS is the same instinct, with satellites for landmarks. Start flat in 2 dimensions. Suppose you know you're exactly 10 kilometers from town A. That puts you somewhere on a circle of radius 10, around A. Now add a second town, B, and your distance to it, a second circle, and 2 circles cross at just 2 points. You're at one of them. Add a third town, C, with its circle. All 3 meet at a single point. That point is you. This has a name, trilateration. Position from distances alone. 3 circles, 1 answer. The whole of GPS is this single idea, lifted into 3 dimensions and run with clocks. One honest wrinkle: real distances are never perfect, so the circles won't quite meet at a single point. They bound a tiny region. Shrinking that region is what all the precision is for. In the real world, you're not on a flat map. You're somewhere in 3-dimensional space. So distances no longer draw circles, they draw spheres. One satellite, and your distance to it, places you somewhere on a giant sphere centered on that satellite. A second satellite gives a second sphere. 2 spheres overlap in a circle. A third satellite shrinks that circle down to just 2 points. And one of those 2 points is almost always absurd, far out in space or buried deep inside the Earth. Throw it away, and the other one is your location. The leap into 3D is hard to picture, but easy to compute. The math is just the flat version, with 1 more coordinate. So in principle, 3 satellites are enough. In practice, 3 won't do, because the distances themselves come from clocks, and one of those clocks is about to betray us. To see why, we have to ask the question we've been dodging. How do you measure distance to something you can't see or touch? The answer is time. Each satellite constantly broadcasts a message. I am satellite 7, and at this exact instant, the time is now. That message races to you at the speed of light. So if you know when it was sent, and when it arrived, you know how long it traveled. It's like thunder after lightning. The longer the gap, the farther away the storm. Here, the gap is the signal's travel time. Multiply that travel time by the speed of light, and out comes the distance. Time becomes distance. From 20,000 kilometers up, that journey takes about 0.07 of a second. Short, but measurable if your clock is good enough. Notice something lovely: your receiver only listens. It never transmits a thing back. The satellites don't even know you exist, so one satellite can serve everyone on Earth at once. There's no limit on users. And the signal is a marvel. Each satellite sends a long, unique, pseudorandom string of bits, known in advance. Your phone generates the same string, slides its copy until they line up, and reads off the delay. That trick pulls the timing out of a signal fainter than the background noise. The message also carries each satellite's exact orbit, so you don't just know when it spoke. You know precisely where it was. Now feel how brutal this is. Light is staggeringly fast, 300,000 kilometers every single second. So an error of just 1/1,000,000th of a second in your timing becomes a position error of 300 meters. A billionth of a second still throws you off by 30 centimeters. To find you within meters, the clocks must be accurate to billionths of a second. That's why every satellite carries an atomic clock, extraordinarily stable timekeeping, drifting just billionths of a second a day. Not the very best we can build, but more than precise enough. With clocks that good in orbit, you'd think the problem is solved. But there's a clock down here that ruins everything. Put it bluntly, if your clock were off by a single millisecond, you'd be placed 300 kilometers away, in another city entirely. Your phone, its clock is cheap and it drifts. Off by even a millionth of a second, and your position would be hundreds of meters wrong. And you can't put a clock that good in every phone. The best ones cost a fortune and draw far too much power. It seems hopeless. Here's the beautiful fix. Treat your clock's unknown error not as a problem, but as one more thing to solve for, a fourth unknown, alongside your 3 coordinates x, y, and z. 4 unknowns need 4 equations, so you simply listen to a fourth satellite. Now the math has exactly enough to solve for your position and the precise error in your clock at the same instant. That is why GPS needs 4 satellites, not 3. The fourth doesn't just locate you. It quietly turns your cheap phone clock into a near-perfect one for free. It's a genuinely elegant trick, an extra measurement that pays for the one thing you couldn't afford. It's also why a receiver, switched on cold, hunts the sky until it locks onto 4 satellites before it shows anything. 3 for where and a fourth for when. Under the hood, it's just 4 equations, 4 unknowns, a little algebra, solved several times a second. And now we reach the part that sounds like science fiction, yet runs every second of every day. We've been assuming a second is a second, the same up there as down here. Einstein showed this is false. Time runs at different rates depending on speed and on gravity. For everyday life, the difference is far too tiny to notice. But GPS demands billionth of a second precision. At that level, relativity stops being a curiosity and becomes the difference between working and useless. 2 effects are in play, pulling in opposite directions. Let's take them one at a time. The first comes from special relativity and motion. The satellites are racing around the Earth at about 14,000 kilometers per hour. And special relativity says something deeply strange. The faster a clock moves, the slower it ticks, compared to one fixed relative to the Earth's center. So a satellite's clock, purely because of its speed, falls behind ours by about 7/1,000,000ths of a second every day. If that sounds too weird to be real, it's measured constantly. In particle accelerators, fast-moving particles live measurably longer than still ones, exactly as predicted. The second effect comes from general relativity and gravity. Mass warps time. The deeper you sit in a gravity well, the slower time flows. Down here on the surface, we sit deep in Earth's gravity well. The satellites, 20,000 kilometers up, sit far higher where the well is shallow. So their clocks, higher up where the well is shallow, tick faster than ours, by about 45/1,000,000ths of a second every day. One effect slows them down, the other speeds them up, and they don't cancel. If that's hard to swallow, you're in good company. A clock higher up genuinely runs faster than a clock below it. It's been measured directly, even between 2 floors of a building. Decades ago, atomic clocks were flown around the world on airliners, then compared with clocks left on the ground. They disagreed, close to the amount Einstein predicted, and later, far more precise versions confirmed it exactly. Put the 2 together. Motion slows the satellite clocks by 7 microseconds a day. Weaker gravity speeds them up by 45. The net result, a satellite clock runs fast by about 38/1,000,000ths of a second every single day. 38 microseconds. It sounds like nothing at all. But remember the brutal exchange rate. Light travels about 300 meters in a single millionth of a second. 38 of them is over 10 kilometers. So leave relativity uncorrected, and GPS positions would drift by roughly 10 kilometers every day. Within minutes, your blue dot would wander uselessly off the map. So engineers bake the corrections straight in. The satellite clocks are deliberately tuned before launch to tick at the wrong rate up there, so they read correctly down here. Here's how real this got. On an early satellite, engineers built in a switch for the correction and ran the clock uncorrected to check. Over a few weeks, the predicted drift appeared right on cue. They switched the correction on, and it has stayed on ever since. Which means every GPS satellite is, in effect, a daily experiment confirming relativity. One that simply has to work, or you'd get lost. Even with perfect clocks, a few things blur the answer. The atmosphere bends and delays the signal on its way down. Cleverly, the ionosphere's delay depends on the signal's frequency, so satellites broadcast on two frequencies at once, and the receiver compares them to cancel that part of the error. The rest, like the lower atmosphere, is modeled separately. Tall glass towers bounce the signal, creating echoes that arrive late. The urban canyon problem that makes city navigation jumpy. So real systems pile on fixes, models of the atmosphere, networks of ground stations, and combining many satellites at once to average out the noise. That's why your phone often uses 8 or 10 satellites at a time, not the bare 4, all cross-checking each other. And GPS isn't alone up there anymore. Russia, Europe, and China each run their own constellations. Your phone quietly blends signals from all of them, which is part of why it locks on so fast. Push it further with a fixed reference station nearby, and you can shrink the error to a couple of centimeters. That's the magic behind self-driving tractors, drones, and survey gear. It's worth remembering where this came from. GPS was built by the United States military during the Cold War, then opened to the whole world. For years, the civilian signal was deliberately blurred. That degradation was finally switched off in the year 2000, and overnight, accuracy jumped several times over, from about 50 meters to under 10. And position is only half of what GPS gives the world. The other half is time itself. Those orbiting atomic clocks are a free, global, incredibly precise time signal, available to anyone with a receiver. Power grids use it to keep their currents in step across a continent. Financial markets stamp their trades with it. Phone networks and the internet lean on it to stay synchronized to the microsecond. GPS has become the world's invisible heartbeat, a shared clock in the sky, every bit as much as a map. Which is also its fragility. So much now depends on these faint signals that a serious outage would ripple through power, finance, and communication, all at once. So look again at that little blue dot. Behind it sits a stack of ideas, each remarkable on its own. The geometry of intersecting spheres, the trick of turning time into distance, a clever fourth satellite that fixes your cheap clock, and Einstein's relativity corrected for in real time. Layered together, working in silence, 20,000 kilometers over your head. Geometry, light, a fourth measurement, and Einstein all conspiring quietly. Just so that you, standing somewhere new, never have to wonder which way to turn.